Thank you for your kind introduction. I'm Takeru Uchikoshi. I'm a master student of Kyoto University. Today, I'm going to talk about experiments using laser. I'm going to divide my presentation into 5 parts. First, I'll give you a brief introduction to my research objective. Conventionally, we conducted experiments on deuterium paradigm system using only electrical stimulation. Then, we have observed a sudden temperature increase and the neutron signal simultaneously. However, there is a problem that the experimental reproducibility is low. So in the present work, we have installed multiple kinds of lasers. The lasers are YAG laser and semiconductor lasers. Lasers can provide several orders of magnitude higher power density. Our research objective is to improve reaction probability and reproducibility by irradiating the deuterium paradigm system with a laser as well as applying conventional electric heating. And recently, we calculated electromagnetic field enhancements on metal surfaces. Then, we observed very large enhancements or energy focusing for the metals commonly used in the community, as shown in these graphs. Such effects may have been unknowingly produced in formally reported experiments. We believe that it is important to actively utilize these effects for the improvements of reaction rates and reproducibility, particularly in electrically or optically driven systems. In part 2, I'd like to describe experimental methods and lasers. These are experimental methods. First, I analyze a paradigm sample to remove residual stress and clean the surface. I analyze a paradigm sample at 1000 degrees for 10 hours under the nitrogen atmosphere. Next, I deposit metal to attach an electrode by electron beam deposition. I attach 100 nanometer thickness golden thin film to the sample. After that, I load deuterium into the sample until the equilibrium by leaving it at room temperature for about 10 hours. Initial deuterium pressure is 760 torr. Finally, I apply voltage and irradiate the laser to the sample in high vacuum. Then, I measure temperature and neutron and do mass spectrometry. In the next slides, I'd like to describe our laser lineup for stimulation. The lasers are 2 continuous wave semiconductor lasers and a pulsed YAG laser. A wavelength, power, and the number of experiments are as follows. This image is using laser in our laboratory. There are 2 sides. Next, these are sample images after experiments. There are 2 sites, the gold sites and the paradigm sites. On the gold sites, as already mentioned, I deposit gold thin film and apply electric bias. On the other hand, the paradigm site, I apply laser during electric heating. The trace of laser can be confirmed on the paradigm surface. In part 3, I'm going to look at results of temperature, and neutron, and mass spectrometry. This graph shows one of the experimental results using a YAG laser. The vertical line shows temperature, input power, and neutron intensity, and the horizontal one shows time. The red plot is temperature. Green is input power. and purple is neutron intensity. Light colors are the reference experiments without deuterium loading. Focusing on the temperature, 90 minutes after the start in the experiment with deuterium, the temperature suddenly increased even though the input power was almost constant. At the same time, we observed the neutron intensity peak. If we focus on temperature around 100 degrees, we can see overshoots in the experiment with deuterium. In summary, we observed a sudden temperature increase with a neutron signal. This slide shows the results of mass spectrometry. This chart shows the relative pressure of mass number 3 and 4 over time. Two factors can be considered here. One factor is that as deuterium amount in palladium decreases, deuterium release rate decreases. The other factor is that as palladium temperature increases, deuterium release rate increases. Balance of these two factors may determine deuterium release rate, with a shift from the former to the latter. At the beginning, the former factor is large and deuterium release rate is gradually decreasing. In the middle of experimental run, the latter factor is large and deuterium release rate starts to increase. This chart added the ratio of mass number 3. This shows that the ratio of mass number 3 is increasing gradually during the experiments. At 0 minutes, that ratio is 0.00716. At 90 minutes, that ratio is 0.0124. So comparing these values, you can see that it is about twice. This result might indicate the generation of helium-3 or tritium. At the bottom image is raw data of Q-mass. At the timing when the absorbed deuterium is almost depressed, if you look carefully, you will see a shoulder peak on the deuterium peak. I think this may be helium-4 generation. This slide summarizes the results of a series of experiments using a YAG laser. As you can see, temperature increase, a neutron signal, and burst of mass number 4 occurred at the same time. We suggest a possibility that the fusion reaction has occurred. In part 4, I'd like to focus on 3 considerations, which are sudden burst of gas species, excess heat generation, and sample deformation. Now, I'll touch on sudden burst of gas species. In other runs, we also observed sudden bursts of mass number 3 and 4. A burst occurs when deuterium is almost gone from palladium, not consistent with the elapsed time. Because different experiments have different temperatures, so deuterium release rate varies from experiment to experiment. Current status, we don't understand this burst well, but it should be noted that the burst occurs at the timing deuterium runs out of palladium, unlikely to the intuitively common gradual decay. Next, I'll discuss excess heat generation. As I showed you earlier, we observed temperature overshoots in some experiments. First, we set up a heat balance equation for the palladium sample. This equation consists of applied power, P in, heat dissipation, P loss, and excess heat, PEX. The variables are represented like these. Next, I explain how to estimate PEX. We determine P loss and CV from reference experiments without deuterium. That is PEX equals 0. After that, we calculate PEX for experiment with deuterium. This figure is an image to calculate PEX. When we calculated PEX, it is resulted in the orange plot in this graph. As you can see, there is excess heat, which is up to about 4 watts. Negative values seen at the beginning of experiments are endotherm due to hydrogen in these. We estimated excess heat generation that cannot be explained only by input power. So our sample weighs about 10 grams, so it has an excess heat of over 350 watts per kilograms. In the next 3 slides, I'll discuss sample deformation. When comparing before and after experiments, we found bending and shrinking of palladium samples. Therefore, we measured XRD. In addition, we calculated potential by embedded atom methods and density functional theory. First, we measured XRD from both sides of the sample before and after experiments. If you look at the figure, you will see the peak shifts only on palladium sides after experiments. Therefore, I think that there exists a distribution of lattice constants and the strain between alpha and beta phases. In summary, palladium samples have an inner mechanical stress, and thus it has a distortion. This slide shows potential calculation by embedded atom methods. We determine the stable palladium sites for hydrogen atoms when the palladium lattice is distorted. In particular, we calculate the potential surface of hydrogen in 110 plane with XY two-dimensional strain. On the left side is the calculation results for palladium of the crystal structure. Stable positions for hydrogen atoms are the places called O sites, represented by blue in the figure. This is O sites. On the right side is the calculation results of distortion states. T sites are stable position in distortion states. The important point here is that stable sites switch by adding distortion. We speculate that switching of stable sites causes active movements of hydrogen atoms, and they may approach each other. And this slide shows potential calculation by density functional theory. We calculated the potential energy with Gaussian software. This time, we calculated with a cluster of 5 palladium atoms and 2 hydrogen atoms. We will show the calculation results of 3 states. The left is ground states, and the middle is the states that palladium is the crystal structure and hydrogen atoms are close to each other. And on the right, palladium is distorted and hydrogen atoms are also close. For the energy relative to the ground states, the crystal structure has an energy 6.7 electron volts higher than the ground states. The distortion state has an energy 3.6 electron volts higher than the ground states. When hydrogen atoms get closer to each other, a distortion state becomes more stable than crystal structure. We suggest that palladium strain may affect the approach of hydrogen or deuterium atoms. What I want to say in this slide is that there are more stable states than crystal structure when hydrogen atoms get closer to each other. And finally, I'll discuss the future works and conclusions. I'd just like to mention our future works. There are two major plans. One is installing liquid scintillator. In previous experiments, we have observed neutron signals, but there are some questions. Are they due to a nuclear reaction, not the natural backgrounds? If a nuclear reaction has occurred, what kinds of reaction? We install liquid scintillator to measure the number of neutrons and their energy. The other one is attaching nanoparticles to the surface of palladium sample. The main aim of this is to provide an even higher density energy. By attaching nanoparticles, it absorbs more energy. As for nanoparticles, we consider not only palladium, but also gold, silver, and so on. And we irradiate laser with the optimum wavelengths for each metal. This is a summary of our results. We conducted experiments using laser in addition to conventional electric heating. During the experiments, we observed a sudden temperature increase, a neutron signal, and burst of mass number 4 at the same time. In mass spectrometry, we observed a particle pressure increase of mass number 3 and 4 film generation as a shoulder peak on the deuterium peak. And we found sudden burst of these gas species out of the palladium sample. Next, we calculated excess heat generation that cannot be explained only by input power. And we found distortion of palladium samples and suggest that distortion affects the approach of deuterium atoms. We would like to thank the financial support by the Thermal and Electric Energy Technology Foundation and the Research Foundation for Optoscience and Technology. That's all for my presentation. Thank you for your attention.
My question is, which one is the resolution of your mass spectrometer?
Sorry?
The resolution of your mass spec.
Mass spec?
Yeah, the resolution.
The numeric resolution of mass over separation.
The separation, because you have you shown data on mass 3.
Mass 3.
As helium-3 and tritium, but it can also be HD, for instance. So, are you sure that this is helium-3 or tritium and not HD? So you should have the right resolution for doing that. And it's much higher than the resolution that we need for separating helium-4 from deuterium.
In our laboratory, QMass is can't distinguish helium-3 or DH or HD.
So it's possible that it's HD.
So it is a very difficult problem. So I have no idea, but we try to distinguish.
Yeah, because if you are eating that surface that is a catalyst and you have H and D inside, easily you can recombine and produce HD that is shown as mass 3.
Okay, thank you.
That's my question. Okay.
I'll take a second here. Yes, it's very difficult to do helium-3 and pretty much impossible in a quadrupole. But you can separate helium-4 from D2. If you give up sensitivity, you can get resolution, and you can also separate them by ramping the ionization potential. So just some suggestions.
Thank you.
And who has the microphone? Okay.
One question about the frequencies of the lasers that you chose. How did you choose them? Was it? To be honest, these lasers are given by teachers.
So, so in the future, I bought optimum lasers.
Just concerning the lasers, are you using them in a pulsed mode or continuous mode? First question. Second question, when you say you observe things, were this in many runs or just in a few? How did it differ from one run to another?
Sorry, one more time, please. Sorry, one more time, please.
Well, the pulse mode or continuous mode for your lasers?
In what mode did you operate the lasers? These pulsed with the YAG laser?
YAG laser is pulsed.
At what rate?
What repetition rate was your pulse frequency? Either way.
This is the YAG laser spec. One shot of energy is 50 millijoule, and we set 10 shots per second this time. And I harvest the output with a lever. So continuous 250 milliwatts.
Is the average. Yeah.
Okay. And when you ran with different samples, you got reproducibly these peaks.
Reproducibility. This is a reproducibility data. Conventional electric stimulation, its number of experiments is 51. The focusing on temperature overshoots, the number of experiments with temperature overshoot is 18. So reproducibility is 35%. Bottom is experiments with using laser. A number of experiments is only 9. The number of experiments with temperature overshoot is 5, so reproducibility is 56%. But number of experiments with laser is less than 10, so it is necessary to increase the number of experiments and collect more data, I think.
Yeah, go ahead.
Thank you very much for this very interesting presentation. Maybe my question is connected with what you are discussing right now regarding reproducibility of helium-4. Is this the same what you said, 35% for electric simulation and 56% for laser? Is this true or this is something else?
I install QMass, mass spectrometry is latest. So conventional electric heating, conventionally electric stimulation is no QMass data. So but from now, I try to measure mass spectrometry always.
Okay, and one more question. When you see the helium-4 peaks, is it the same places where neutron also is detected?
No neutron.
No neutron.
This using YAG laser experiments is same time. After 90 minutes, we observed helium-4 and neutron, and the sudden temperature increases. This is the same time. This one shows about, but really differences. 99 minutes and 101 minutes observed for helium generations. So little differences are there.
Okay, Peter.
So could you remind me how you loaded your samples, and do you have some idea of what loading you achieved?
Loading?
Deuterium loading.
Deuterium and palladium.
Deuterium and palladium. About 10 hours at room temperature.
No, the concentration.
Ratio. Okay. Deuterium is 99.6%, and 0.4 is hydrogen.
So about 0.7 loading.
You did this at atmospheric pressure, so you just have.
Mass pressure.
So do you know the concentration of deuterium in palladium?
Okay. In palladium is approximately 0.7.
Okay.
Do you know if the distortion of the lattice stopped your anomalous results?
Did that, the distortion,
Distortion.
did it change when you got excess heat or?
This is very complicated. This is complicated thing. So I think that deuterium is a loading or release, and alpha or beta changes. So distortion is occurs, I think. But excess heat is I have no idea.
Were you able to continue to get an anomalous result, excess heat, or did it just stop after a certain point, maybe possibly pointing to a damaged lattice?
When you turn the laser off, did the heat stop, or did the heat stop before you turned the laser off?
Now, laser is irradiating laser is during experimentation all the time. So it's turn off. I don't measure temperature. If turn off the laser, I don't measure temperature. So I think that the excess heat generation or a reaction is not occurs. It's turn off the laser.